So here are the 5.2 Day 1 notes. This is graphing simple rational functions. Listed here are our objectives. The first one is to state that a rational function is one whose form is f of x equals p of x divided by q of x. You'll be able to identify the parent function for simple rational functions, which is f of x equals a divided by x. You will also be able to describe the transformations given a rational function in the form f of x equals a divided by x minus h plus k, and also explain how they affect the asymptotes. Write the equation of the asymptotes given a rational function in a different form, f of x equals ax plus b divided by cx plus d, and then use interval notation to express the domain and range of rational functions. Now let's talk about what is a rational function. Well, a rational function basically is the function in the form f of x equals p of x divided by q of x. Basically, these two, p of x and q of x, are polynomials. Now remember, you guys learned about polynomials last semester. That could be linear functions, right? So you could have 3x, or you could have 3x squared. That was our quadratics. You can even have 3x to the third power. So those are kind of some examples of polynomial functions. Now, when we graph rational functions, basically what it's called is a hyperbola. That is the graph of rational functions. Now here, what we have is the function of f of x equals 1 divided by x. Now notice here that we now have actually two parts to our graph, and they kind of look like exponential and log functions, what we dealt with last unit. So here we'll have two parts to our graph, and now instead of just having one asymptote, we're going to have two. We're going to have a vertical asymptote at x equals 0 and a horizontal asymptote at y equals 0. Now these asymptotes are only for our parent functions. Okay? Whenever we have translations, our vertical and horizontal asymptotes will also change. Now the parent function for rational functions is going to be in the form of y equals a, where a is just a number, so it could be either positive or negative, over x. A just tells you if either our function flips or if there's a vertical stretch or shrink. Now here we're going to have branches. Basically, branches just means there's two symmetrical parts of the graph of a hyperbola. As you can see, we have our two symmetrical parts here. Okay, let's go ahead and graph a function. So our first function we're going to graph is y equals 6 divided by x. Now here, what we're going to do is create an xy table and plot these points onto our function. Now this y equals 6 divided by x is in the form of y equals a divided by x, which we know is our parent function. So the default asymptotes are vertical. It's going to be at x equals 0. Okay. And our default horizontal asymptote is going to be at y equals 0. So whenever you have the parent function, these are your default asymptotes, as we have dealt with before when we did logarithms and exponential functions. So let's be y equals 0. So no points will be on these lines, and our graph should never pass these lines. So let's go ahead. We're going to pick some x values to plug into here. I'm going to go ahead and start with -3, because -3, if we plug into there, right? If we plug -3 in for x, basically all we do is 6 divided by -3. Well, that should just give us -2. So we're going to plot that point. So we go over 1, 2, 3, down 1, 2. Okay, then we do -2. So 6 divided by -2, that should give us -3. So I go over 1, 2, down 1, 2, 3. -1 should give us, because if we do 6 divided by -1, we get -6. Now I'm just using these x values because they go into 6 evenly. If you wanted to start at -6, you could have done that as well. So let's go to -1, -6. I'm going to scroll down here. So I go over -1, down 1, 2, 3, 4, 5, 6. Okay. Now remember here, if we put 0, right? If we plug 0 in for x, 6 divided by 0. Remember, whenever 0 is in the denominator, that makes the function undefined. And that's actually where we have our asymptote. So there's not going to be any y values because that is where our asymptotes are at. That means we need to start up at a positive value. So we're going to start up at 1 now. So we do 6 divided by 1 to give us a 6. So I go over 1, up 1, 2, 3, 4, 5, 6. Then I'm going to pick 2. So 6 divided by 2 should give me 3. So I go over 1, 2, up 1, 2, 3. And I'll pick 3 as well. So 6 divided by 3 gives us 2. So I have 1, 2, 3, up 1, 2. Now we're going to use the same shape that was in the last function. I'm going to quickly go over there so we can see what that looks like. Now notice what our graph looks like. See, on both sides it's getting very close to our asymptotes, as well as the second half here. Okay? So when we're graphing this y equals 6 divided by x, we're going to get very close to the asymptote, but never touching it. I'm going to connect the points. So this one goes down here. And in my first quadrant, it comes up like this. So it kind of looks like a decaying, right, exponential, and this looks like more of a logarithmic function. Okay. So this is basically the graph of y equals 6 divided by x. Now comparing this to 1 over x, right, we've expanded this a little bit because the 6 tells us we either have a vertical stretch or a shrink. Okay, so we expanded it here. Okay, now that was of our parent function. What happens now if we have this type of graph, y equals -4 of x plus 2 minus 1? Well, realize this is the graph of y equals a divided by x minus h plus k. So remember, a kind of just tells you either there's a vertical stretch or shrink, and it tells you if there's a reflection. Now, like we've done with other functions, h and k, h tells you if there is a translation either to the left or to the right. Remember, opposite of what you see. K is once again a translation that goes up and down. Okay? So what we're going to do, just like we've done before, we're going to first graph the parent function. So I'm going to use PF to represent parent function. And remember, our parent function is in the form of y equals a divided by x. Well, in this case, if we look at a graph, -4, which is on top, that is our a value. So we have -4 over x. So now we're going to do an xy table and plot these points. Now, before we do that, we do want to make sure what our asymptotes are at. Because we're graphing the parent function, remember, the asymptotes are defaulted at x equals 0 and y equals 0. So I'm going to go ahead and do my asymptotes so I know what points can't be touched. And then don't forget your second one. Remember, there's always 2 asymptotes for rational functions. Okay, now we're going to plug values. Here, let's plug in -2. That should be a good value. So we plug -2 in for x. We do -4 divided by -2. Well, that should give us a +2. I'm going to do -1. So if I plug -1 in for x, -4 divided by -1 should give me a +4. Now remember, 0, just like the last graph, if we plug that into our x, well, -4 divided by 0, that's undefined. that's actually where our asymptote is at. So here we can't have any y values associated with our x of 0. Okay, let's think about 1 now. Negative 4 divided by 1 gives us negative 4. And then if we plug 2 into here, well, negative 4 divided by 2 should give us negative 2. Now also notice that the numbers repeat. The only difference is the signs. So the numbers repeat, but your signs are going to be different here whenever you have the parent function. Let's go ahead, we're going to graph these points. So I go over 1, 2, and then I go up 1, 2. Okay, negative 1, and then I go up 1, 2, 3, 4. And then 0, remember nothing there. Now I go over 1, I go down 1, 2, 3, 4, and then 2, down 1, 2. Okay, so now here it looks like because the points are coming up, we're going to kind of have like an exponential growth here. Okay, so we're going to have our first part of the graph coming up like this, and then our second part of the graph, because remember, our asymptotes, our graph is getting really close to those asymptotes, so getting close to the horizontal, and then getting very close to the vertical. Okay. I'm going to make those points a little bit darker so you know where they were. There we go. So basically, this is what our parent function of the graph looks like. But notice here that we have translations. We have an x plus 2, okay, and then a minus 1. Now remember, anything with x, that's going to be our, basically our horizontal translation. Now since we see a plus 2, that means we're actually going to go to the left 2. So with our function, we have to go left 2. And then because we have minus 1, that's exactly as we see it, we're actually going to go down 1. Now with our translations, we also need to move our asymptotes. So our vertical asymptote, that's going to be dealing with our x value. So we started at 0, but since we're going left 2, I need to move my asymptote over 1, 2. So my new asymptote with my function is now going to be at x equals 0. So I'm going to say the VA, which stands for vertical asymptote, is at x equals negative 2. And let me elongate this. Okay. Now, not only do we move our vertical asymptote, but we also move our horizontal. Now, the minus 1, that deals with your y. So the r, basically our horizontal asymptote, which we need to move down to our minus 1. Now, I changed this HA, which represents horizontal asymptote. The equation for this, remember, don't forget your equation, is now going to be at y equals negative 1. So now, I've done that. I'm going to move each of my points to the left 2 and down 1. So the green, okay, that was part of our original. So I'm going to move my green over here, go over 1, 2, and then down 1. So now these are going to be black here. Okay, same thing. Right here I see a green point. I'm going to move that to the left, 1, 2, and down 1. Now, we use the same shape. The shape does not change. Okay, so now our graph is getting close to our vertical and horizontal blue asymptotes here. And notice that my shape stays the same. Okay, now I need to move these points. Same thing. You go to the same way. We move to the left 1, 2, down 1. And same thing, 1, 2, down 1. Once again, the shape stays exactly the same. The only difference is now our points. So the black is now our function of y equals negative 4, x plus 2 minus 1. And the blue lines, that represents our new asymptotes. Now, using this information, we need to find the domain and range. So I'm going to go ahead and go down here so we can have domain and range. Now remember, domain deals with your x values. This is actually going to include our asymptotes here. Now, notice here that we do have some negative values, but we stop at our vertical asymptote at x equals -2. So because we have some negative values, we do start at -infinity, and we go to our vertical asymptote, which is at -2. And we do union sign because we're going to go from -2. And notice here with our black down here, this graph, we also get positive x values. So we go to positive infinity. So because we now have two parts of our graph, we're going to have two parts for our domain. So we're going to go from -infinity to our vertical asymptote, which in this case was -2. Then we start back up from our vertical asymptote to positive infinity. This is usually going to be the form for our domain. Our range is going to be very similar, so we're also going to start at -infinity, because notice we do have negative values on our y, and we go to our now horizontal asymptote. So our horizontal asymptote is at -1. We do union sign, and then we go from -1, and notice we do also have positive values, so we go to positive infinity. So just like with the domain, we have two parts to our range. It goes from -infinity to our horizontal asymptote, and then horizontal asymptote to infinity. So I'm going to go ahead and put that there so you guys know that you will always include your vertical and your horizontal asymptote in your domain and range. And remember, we put parentheses around our asymptotes because the graphs never touch and never cross those asymptotes. So here's the domain and range of our function. Okay, now let's go to our next form. Here we have graph y equals 2x plus 1 over x minus 3, and once again we have to state the domain and range. Now this is a little bit different because we don't have a number, just a number up in our denominator. We now actually have a function, a polynomial, 2x plus 1. So here we're actually not going to do a parent function. We're actually going to graph the function we see on the screen right here. Our first thing we have to do is actually find the asymptotes. Okay. Now, in order to do that, we're going to use this form to help us out. So the general form for this type of function or rational function is we have y equals a times x plus our b. That should look kind of familiar, right? A linear function. And then we have cx plus d. So it's like two linear functions as a fraction. So find asymptote. Well, let's figure out our VA. Remember, that's our vertical asymptote. To find our vertical asymptote, we are actually going to look at the denominator. Basically, whatever makes our denominator 0, that's going to be our vertical asymptote. So I'm going to write down that right here. So whatever makes, that's a make there. So whatever makes the denominator equal 0 is going to be our vertical asymptote. So in order to know what makes our denominator 0, we're going to take the x minus 3, which is in our denominator, and set it equal to 0. Because remember, our vertical asymptote is still an equation. X equals a value. So now I'm going to solve here. So I'm going to add 3 to both sides, so I get x equals 3. So my vertical asymptote here is going to be at x equals 3. I'm going to go ahead and draw that. There we go. I'm going to scroll down just a little bit so I have my vertical asymptote going all the way down. There we go. So x equals 3 is our vertical asymptote because that number is what makes our denominator 0. So you will do that every single time when you have this form to find your vertical asymptote. Now to find the HA, which is our horizontal asymptote, we're going to do something a little bit different here. What we're going to do is we're going to take our, it's going to be y equals, remember, because horizontal asymptote. We're going to take our A value and divide it by our C value. That's going to be our horizontal asymptote. So notice in our general form, we have AX and then CX in the denominator. So we go to our form here, or our graph, 2x plus 1 divided by x minus 3. Our A value in this case is going to be 2. And know that the coefficient in front of our x here is going to be 1. So we have 2 divided by 1, which that should just give us 2. So our horizontal asymptote is going to be now y equals 2. So you'll always use this form, A divided by C, to find your horizontal asymptote. So I'm going to come here at y equals 2 and draw my horizontal asymptote. There we go. Now that I've drawn my vertical and horizontal asymptote, the second thing I'm going to do is now do an XY table. So I'm going to go ahead and scroll down. Now make sure if I'm going too fast or if you need to slow down the video, make sure you either pause it or just slow it down a bit so you can get all this information. Okay, so I'm going to come down here. 2 is our table. So we're going to have an XY table. So this might be where you want to use a calculator, so might make it a little bit easier. Now here, basically you want to pick points, right, that corresponds to your asymptotes. So you're not going to pick any maybe values that in which our asymptotes do not work at, okay? So let's go ahead. You can pick -2 if you want to. Use those 5 points. -2, -1, 0, 1, and 2. I'm just going to pick these points here. I'm going to pick 1, 2, 3, 4, and 5. Basically, it's a little bit of a trial and error for which points you pick here. Okay, so what we're going to do is we're going to plug 1 into our function. So we plug 1 in for x here and plug 1 for x here. So we do 2 times 1, well, that should give us 2. So 2 plus 1 gives us 3. And then in the denominator, we get 1 minus 3 to give us a -2. So we basically get -3 halves, or -1.5 if you want to write it as a fraction. Now 2, I plug 2 in for here. That should give us 4 plus 1, which is 5. And if I plug 2 down here, 2 minus 3 gives us a -1. So basically I get 5 divided by -1, which really should give me -5. Okay, if I plug 3 into there, so 2 times 3 gives me 6. 6 plus 1 is 7. And then if I plug basically 3, but remember 3 minus 3, that doesn't work, right? Because that is our vertical asymptote. So here I'm going to just draw a line because we can't have a y value. So now we go to 4. So I plug 4 into here, so 2 times 4, that gives me 8 plus 1 is 9, and then 4 minus 3 should give me 1. So here I get 9 divided by 1, which should just give me 9. So you can see that I'm picking numbers that kind of give me something nice in the denominator, nothing too crazy, okay? And then 5. 5 times 2 gives me 10 plus 1, which is 11, and then 5 minus 3 gives me 2. So I basically have 11 divided by 2, which is also associated with 5.5. Okay. Now, you don't have to use the same x values that I use. You can use any other ones, and they should give you points that will work. So let's go ahead and plot these. So we have 1, -3/2. So remember, 1's our x, and then -3/2. That means I go down 1.5 here. 2, -5. So I go over 1, 2, down 1, 2, 3, 4, 5. Then I have 4, 9. So I go over 1, 2, 3, 4, up 1, 2, 3, 4, 5, 6, 7, 8, 9. And then lastly, we have 5 and 5.5. So I go over 1, 2, 3, 4, 5, up 1, 2, 3, 4, 5.5. Now notice, because of the x values I picked, I was able to have 2 points on this side, basically on the right side of my graph, and then 2 points on my left-hand side. So 2 points, that's basically what you want to get. 2 points on your right-hand side when you're graphing these rational functions. And then 2 points on the other side so you can graph it. And remember that both of the sides should be going or approaching your asymptotes. Okay. Now our last thing we need to do is we need to figure out our domain and range. Oops, I'm going to put that for D. So here's our domain. Now remember, domain basically goes from -infinity all the way to our vertical asymptote. So we said our vertical asymptote was at x equals 3. So we're going to go from -infinity to, oops, that should be 3, -3. Should go from -infinity to 3. Don't forget the union sign. And then we pick it back up from our vertical asymptote at 3 to infinity. Then for our range, the range deals with our horizontal asymptote. I'm just going to go up a little bit. We found our horizontal asymptote was at 2. So remember, using the same form here, we go from -infinity to our horizontal, which is 2, and then union sign, from 2 to infinity. And so that's how you would graph a rational function in the form of y equals ax plus b divided by cx plus d. And remember, if you need to ever pause the video so you can get all the information, that's always a good idea to do. And then there's our domain and range down there. Okay, so for our last problem, it's going to be a word problem here. So example 4, it says a 3D printer builds up layers of material to make 3-dimensional models. Each deposited layer bonds to the layer below it. A company decides to make display models of engine components using a 3D printer. Now the printer itself costs $24,000, and the material for each model they make costs $300. Our first thing we need to do is write an equation that gives the average cost per model as a function of the number of models printed. So the first thing is we need to identify our variables. So here I'm going to use C, and that's going to represent our average cost. While M is just going to be the number of models. Okay, now here they say write an equation that gives the average cost of the model, so our C, as a function of the number of models. Now, yesterday you guys just learned about direct and inverse variation. We're here is going to use a inverse variation with our variable C and M. So we're going to use inverse. Okay. We're going to use our inverse variation to represent C and M. There we go. So we'll have C equals, now it says the material for each model costs $300. So like if you have one model, the material costs $300. If you have two models, then you would have to do your 2 models and multiply it by 300, which gives you 600. So how we're going to do this, we're going to do 300, okay, and we're going to multiply it by our m, because, of course, 300 times m gives us how much the material cost. Now, you also have to tack on, well, how much does the printer cost? The printer is basically just $24,000. Now, remember, whenever we did inverse variation, it was our y equals k divided by x. So, not only do we have the m in our numerator, but because we're doing an inverse variation, we will also have m in the denominator. Because basically up here is our k, and in the denominator is our x, if you're thinking about inverse variation. So we have our equation as 300m plus 24,000. This kind of just gives us the cost of, depending on the number of models. And remember, because we're also doing average, you divide by how many models there are. That's why we have to use inverse variation, because we're dividing by how many models there are. Okay, so the next thing is we would have to graph the function and then use the graph to estimate how many models must be printed for the average cost per model to fall to $700. So we know that the average cost is going to be at 700. We're going to plug that 700 into our C spot. So basically what we're doing is we're solving for m here. So we have 700 equals 300m plus 2400, or 24,000, excuse me, divided by m. Just like we've done before, we're going to plug this into your calculator. Make this, you can say this, our y2, and then our equation as y1. So you will be needing a graphing calculator for this. So let's go ahead and plug this into our calculator. So 700 is our y2, this is our y1. So go to your y equals. I already have it in here. Now remember, we only deal with x's on our calculator. So it's going to be 300x plus 24,000. Now notice, because we're dividing, I put parentheses around my 300x plus 24,000. If you do not do this, or make it into a fraction, you're going to get the wrong graph. And then I have to divide it by x, because remember, that's our m. And then my y2 is basically 700. Now we're going to see with our window, so I just did a standard window of -10 and 10, and then scales 1, -10 to 10, 1. Let's see if this is going to give us what we want. So I graph it, and we don't see anything. Well, that means we need to change our window. Now here you might have to kind of play around to get what your window is. I'm going to go ahead and tell you that maybe one good window would be from 0 to 70. That would be from your X-min to X-max. And then scale of 10. And then for your Y-min, 0 to, let's say, 25,000. And then make your scale 5,000. Of course, you can always do a different window as long as you can see the graph. And so here we can see we have our part of our hyperbola, and then here we see a line. Okay, so that means we can see that they'll intersect. So remember, to get our intersection point, we get second trace. We go to intersect, enter. Make sure you just press enter 3 times, 1, 2, and 3. And then we get x equals 60 and our y equals 70. So basically, when it says use the graph to estimate how many models must be printed for the average cost per model. So let's go ahead and graph our function here. Okay. So we basically had our graph. And also notice that we're actually going to have an asymptote at 300, at y equals 300. Because using that form of a divided by our c value, that gives us our horizontal asymptote. And then here, we're just going to say this was our 60 and then 700. So that means m must equal 60. Lastly, it says, what happens to the average cost as more models are printed? Well, here, as I said before, we have an asymptote at y equals 30. Because if we're using that form we did last time, we can take our a value and divide it by our c. Basically, that means as the cost, we have more models that are printed, basically that means that the average cost per model approaches about $300. So that's basically what's happening there. Okay, so your homework for this is on Google Classroom, so make sure you check that out. If you have any questions, make sure you come in before or after school to get help, or you can email me, and your homework will be due the next day. And remember, if you ever need to pause this video or slow it down, make sure you do that so you understand and get all the information down.